All right, so as we start every week, this is Intro to Statistics. Make sure you're in the right place. I don't want you all to be in the wrong place. And this week, we are continuing our conversation on inferential statistics. In particular, we're going to be looking at normal distributions and some of the mechanisms involving normal distributions. All right, last week, we spoke about probability, and that probability conversation will tie into our normal distribution conversation because we're going to look at a way to basically find the probability of any value, or basically of hitting a certain point. It'll make more sense as we kind of dig into it, but that's basically what we're going to be doing today. So, as usual, we have collected, organized, and presented data just so you can get a framework of where we are in the class. And we are answering the question. These last couple of lectures and the next couple of lectures are answering the question of what do we do now, right? That's what these questions are answering. So going back, just a recap of our inferential statistics with our bowl of soup, our pot of soup, cooking the pot of soup, take the spoon out, taste it. Basically, we're at the point where we're trying to say, what does that one spoon of soup that we took out tell us about the entire rest of the pot? Right, that's what we are. And again, this is the same example we've done. We've done it over and over again. This is just to help you frame this conversation. So we're going to start our conversation by looking at what we call continuous distributions. Right, continuous distributions. With a continuous distribution, it's basically a distribution where the values are kind of smooth all throughout. Right, so anytime we have a continuous variable, right, and our values are smooth all throughout, meaning that we're not, or at least we don't expect gaps in the way that we measure it. Right, so it's not like 1, 2, 3, 4. That would be discrete. Right, so a lot of the probability examples that we looked at last time were discrete. We were looking at examples where how many heads can we get on 5 coin flips, right? How many heads can we get? Well, what's the probability that we get 3 heads or something like that, right? And that would be getting 3 heads out of the 5 coin flips that we do. And that's discrete. They're individual numbers. You can't get 2.5 heads, right? You can't get 1.23 heads. On the other hand, if we were to measure something like height, so like we did do an example, we were looking at insurance. With the insurance one, that also wouldn't be continuous because either you have health insurance or you don't have health insurance. So that's not continuous either. Similar thing to what we looked at with when we were looking at relapsed or not relapsed in the drugs. Either you relapsed or you didn't relapse. There's no in between. There's no middle ground there. Either you did or you simply did not. With continuous distributions, on the other hand, let me erase what I wrote up there. With continuous distributions, on the other hand, when we're measuring things that are continuous, there isn't a gap in our measurement, right? So, for example, in one of the examples that we will kind of come back to a lot because I think it's so easy to understand, is like people's heights, right? So here, let's say we took a histogram of people's heights, and this was a histogram that was showing the distribution of heights in the US, right? And as you can see, going all the way from 140 centimeters all the way up to 200 centimeters, right? Somebody could take on any height from 140 centimeters to 200 centimeters. Like, there's nothing that stops you from being 140.25769 whatever centimeters, right? You can take on any height. So there's not really a way of saying, let's say we wanted to ask ourselves the question, what's the probability that someone is 160 centimeters? How would we do that? Like, anybody have an idea? What's the probability? And let's use feet, for example. Let's say we were in the classroom and somebody's going to walk in a couple of minutes. We hear them coming down the hall. And we want to know, we have our histogram here. We want to know what's the probability that the person that comes into our class is 6 feet. Exactly 6 feet. What's the probability? Anybody have any ideas there? Like, how could we find out that probability? Probability that someone is exactly. So that means they can't be 6 feet and 1/16 of an inch. They can't be a hair taller than 6 feet. They can't be a hair shorter than 6 feet. They have to be exactly 6 feet. What would that probability be? Anybody have an idea? Anybody have an idea? So I'm not hearing. Oh, go ahead, Gloria.
I'm sorry, but we say that it's one out of the amount of students that we have in the class, or are we basing this off of just knowing the heights of the people in our classrooms?
Well, I mean, we did some study of all of the people at Trinity or whatever, So we got information, we got data. Remember, we had a couple of ways of finding probability. But basically, we were doing probability as the amount of times what we want to happen happens divided by how many things we observe altogether. Right? But that was for situations where we were like flipping coins and stuff. How do we know that someone's going to be exact? I would go as far as to say the probability that someone walks into a room and is exactly, now remember that word, exactly, like not a little taller, not a little shorter, not basically, not approximately, exactly 6 feet, not a hair shorter or taller, right? I would say that probability is probably close to zero, if not exactly zero, that someone is exactly 6 feet, right? That probability is really, really, really low. Why is it really, really low? Because if you measure someone, it's not likely that they're 6 feet tall. Like, exactly. It's not likely that someone's height is exactly anything, right? That's not very likely, right? Just because, I think it's just because kind of the way the world works. Things in the world are not exact in that manner, right? So what we do with continuous distributions instead of looking and saying, oh, what is the probability that someone is exactly a certain thing or something is exactly a certain thing? When it's continuous, meaning it can take on any value in the range, right? We instead measure the probability that something is between two values. So here, this shaded blue thing, right? That is measuring the probability, right? That someone is between 180 and 185 centimeters, right? Or in our number system, 180 centimeters. 5 feet 11 and 6 feet 1, right? That's what we're measuring. And that kind of makes more sense because if you were to guess that someone was between a certain range of heights, you could say, okay, I would bet that the person who's going to come into our classroom is between 5 feet 8 and 6 feet. That's a good, like that would be something that would make more sense or be a little easier to say that, like that would be a more valid guess if that makes sense versus saying we're trying to find the probability that someone's exactly a value. And with this is basically what we do with continuous distributions. We find the probability that something falls in a range of values, not the probability that something hits an exact value. So that's what we're finding when we do continuous distributions. A range of values. We're always looking at a range. So anytime you see this word continuous, right, you should be thinking that we're looking at a range of values, not one exact value. Right? Not one exact value. Now, with this, all of the data, right, all of our data is all of this stuff right here. Right? All of this represents all of our data, and then even all of this over here on this side too. All of that represents all of our data. Remember how we defined probability? We said probability was going to be, when we did our frequentist approach, we said we were looking at probability as the number of favorable outcomes, right, divided by the total. That's not total. We're just going to pretend like that says total. Total number of outcomes, right? That's what we're measuring when we do probability. Number of favorable outcomes divided by the total number of outcomes. So when we look here, each of these bars of our histogram represents a certain number of people that fit in one of these categories. Right? Each of these bars, each one of them represents a certain number of people that fit into one of our categories. We want to know the probability that someone's in this category and this category, or this category. Right? So what can we do? It's almost like we're taking these two categories here, right? We're taking these two categories, and that's going to be our favorable outcomes. And then everything else is going to be the total number of outcomes. Right? So it's almost like we're doing that. So we're looking at how much, what proportion of our data, what proportion of all the people that we've measured fit into these two categories. And that proportion becomes our probability, right, that someone is in those two categories. And another way of looking at that proportion would be to look at the area of that section. And that would be another way of looking at it, looking at the area. Because we're looking at the area of that section versus the area of the entire thing. Right? So when we do, and this is good framing because we're understanding this connection between area and probability. And when we have a continuous distribution, we're basically saying this red section is what we're looking for, and the orange section is the whole mass, everything, right? So that's kind of what we're looking at here. And again, it's back bringing us back to that same idea of the number of favorable outcomes divided by the total number of outcomes. Okay. So moving on, when we have a continuous distribution, when we have a histogram, and we want to make it into, or kind of make it look like a continuous distribution, we need to draw a smooth curve that connects all of the peaks of the histogram. And we can see here, that this smooth curve on this one, it's kind of almost normal. And what we'll find is that when we actually do that, where we're trying to like draw a curve to represent the histogram, that curve that we draw will almost never look exactly like not exactly, like perfectly like one of the curves that we've seen before. And it's up to us to kind of make certain approximations as to, what kind of shape it is, or in terms of describing the shape. And the curve, this thing, right? The curve, we call that curve our probability density function. That's what we call that curve. Our probability density function. And the reason why it's a probability density function is because this curve is telling us something about how much of the probability is condensed in a certain place. So looking at this curve, which do you think is more? What do you think is more? The probability that we land in this section, we'll call that section 1. The probability that we land in this section, we'll call that section 2. Or the probability that we land in this section, we'll call it section 3. Which probability do you think is the biggest?
2.
2. And why do you think 2 is the biggest? It's not rocket science. Because it's what? Why would 2 have the largest probability?
Because it's the center.
Not because it's the center. No, not necessarily that.
Well, that's where most of the data is condensed at.
Okay, I see what you're saying. Yes, most of the data is condensed in the middle, but I mean, I could have drawn my lines a little differently. What makes you say that two has the largest probability? What is it about the section two that's different from one and three? Yes, it's in the center, but what else? There's something very
It's
obvious.
it's the largest section.
It's the largest section. That's literally what it is. It's the largest
The height.
section, right? It has the largest area. Like the space there in the middle is the largest space that's there, right? It's the largest space. So imagine if you were playing a game of darts, which section would you have the highest probability of hitting? The largest
Two.
section, right? Two, section two, right? So these are all analogies that you can use to kind of make that connection between area and probability. And this is our probability density curve because we can look at certain areas of the curve and see how high up did the curve go. In the places where the curve is going higher up, that means we have a higher probability of being there, of landing there, because there's more space. And the places where the curve goes lower and lower and lower, it means we have a lower probability of landing there because it's less space, right? So this is our probability density function. Um, so again, which we kind of already talked about, we're looking at the area. So imagine you were playing darts, right? We would be looking at, and we wanted to land in this blue section. What we would care about is the area of this blue section. That's what we would care about. What's the area of this little section right here? Well, now it's red because I colored it red. Right? What's the area? And that area becomes the probability of us landing in that section, or the probability that someone random or someone we sampled lands or is in that section. That's what that area becomes. Um, because the probability of a section is the area under our curve, or how much space is under our curve, and this is kind of what we talked about intuitively. The probability that we hit any exact value is zero. Intuitively, like we can intuit that hitting an exact value is going to be really, really small, if not impossible, which is what we said intuitively. But here we're getting that by definition, the probability that we hit any exact value with a continuous distribution is zero. So if it's continuous and we want to say find the probability that someone hits a certain point exactly, that probability is always going to be zero. Because when we deal with continuous distributions, we always need to be looking at a range. We always need to be looking at a range of values, not an individual value. So what we often do, and what we can often do, is we can often take our continuous distributions, and when they are almost in the shape of a normal distribution or bell-shaped curve, we can approximate them as normal distributions. So like we can see this one, this is pretty symmetrical. Like, no, it's not exact. We got this little dip section over here, but it's not that much of a it's not that much of a big deal because it looks pretty symmetrical. We would describe this as symmetrical or normal or basically normal or approximately normal. So again, our normal distribution, which is probably our most important distribution, our most important of the continuous distributions that we'll look at, right? Our normal distribution, which is also called unimodal, symmetric, bell-shaped. Our normal distribution um, looks like this. That's what it looks like, right? It looks like a bell, pretty much. And the way we represent a normal distribution when we have one, right, is with an N and that and that. What do these two symbols mean? What's that one mean? And what's that one mean?
One is median.
Nope, not meaning. So
Me-
mu is the mean, and sigma is our standard deviation. So basically, when we want to represent a normal distribution, we need to list what the mean is and what the standard deviation is. Now, note we're listing the population values. We're listed the population mean and our population standard deviation, right? But that's what we need to list. We need to list the mean and the standard deviation when we represent a normal distribution. So if we say something is a normal distribution, you should also list the mean and the standard deviation. Let's look at an example. So here we have the heights of males, and this is a study looking at male heights in real life versus male heights on OkCupid. And what they found is that across the board, what guys would do is this. Here's the curve that represents male heights in general. That light blue curve, that light purple curve. I'm sorry. And then here's the curve. The darker purple curve is the representation of male heights on OkCupid. See it? And what do you notice? What shifted from the light purple to the darker purple one? What shifted? Anybody? What's the difference between our light purple?
Is taller.
Say that one more time.
I guess the peak is, I don't know, but it's like it seems like it's going up or to the right, or they're taller.
Well, look at it. It went. Look at our peak here, right? This middle point is like the mean or the middle point. We were here and now we're here, so we went across. It shifted up, right? That it's like the average height got bigger. All of these people shifted which way? They all shifted that way. See? Everybody shifted that way. Everything shifted a little bit higher. Why do you think we saw something on OkCupid is a dating site? Why do you think there was a shift in the heights? Why do you think
People lied about their height.
people was lying about their heights? That's exactly why people were lying about their heights. To kind of, I guess, I don't know, get more dates, right? And what they actually saw is that as you got closer to like 5'8", that's when people started lying more. Guys started lying more, right? So if you're like 5'8", you're more likely to be like, I'm 5'10", I'm 5'11". Well, you can't be 5'8" saying you're 5'11". That's just wrong. But as they got taller, people were more likely to start shifting their heights up a bit more. You know what the funny thing is? They actually found that women do the same thing on the dating site, which was weird, but women also exaggerate their heights, which kind of makes me think maybe it's just that people don't know how tall they are. Because I don't know. In my head, women kind of don't want to be super tall, like for the most part. Obviously, everyone's different, but that's what it is in my head. You're not trying to be taller. But yeah, that's what they found, that women also exaggerated their heights and shifted it up a little bit to make themselves a little bit taller. But again, it makes me think people don't know how tall they are. Because I know when I go to the doctor, I usually have like a little short nurse, and at least the last couple of times, the little short nurse, she tries to reach up and measure how tall I am. And like she can't see because she's shorter than me. So she's not like getting a good sight. So because she's looking up, the nurse is always like, "You're such and such tall," and I'm like, "Okay, good. I'm gonna stick with it. That's my story." So maybe people just don't know how tall they are. But this is an example of us kind of looking at something that was not a normal distribution. Exactly. You see this light purple line? That light purple line is like what we got back from our study. And then we're kind of approximating it with the darker purple line. See the dashed purple line? That's from the study. And then the dark purple line is what we're approximating it as. Right? So again, we have our normal distribution. And when we have our normal distribution, we can have different normal distributions with different parameters. Because again, the two parameters that really matter when we have our normal distribution are what? The standard deviation and the mean. So here we have normal distributions that have a standard deviation of 1 and a mean of 0. And here we have normal distributions that have a standard deviation of 4 and a mean of 19. Right? That's what we have here. Standard deviation of 4, mean of 19. And what we're actually going to do, we're going to later look at what we call standardizing normal distributions, which will basically be making all of our normal distributions have standard deviation of 1 and a mean of 0. So let's look at this. So SAT scores are distributed nearly normally with a mean of 1,500 and standard deviation of 300. ACT scores are distributed nearly normally with a mean of 21 and a standard deviation of 5. A college admissions officer wants to determine which of the two applicants scored better on their test with respect to other test takers. Pam, who earned an 1,800 on her SAT, or Jim, who scored a 24 on his ACT. Right? So that's the question. Who scored better? Who did better on their test? Did Pam do better on her test relative to everyone else, or did Jim do better relative to everyone else? What tool could we use to compare their scores on each of their different distributions? Anybody? Oh, y'all need a refresher. Oh my God. We're looking at relative standing. Something from our relative standing section. What could we use to compare the two from relative standing? All right, I'm gonna just tell you. Z-score. Right? We can use the Z-score to compare the two. Right? We can compare the two with the Z-score because the Z-score is going to kind of just say how far each of them is away from the mean. And the person who is further away or more above the mean did better relative to everyone else. So we need to calculate Pam's Z-score and calculate Jim's Z-score. So again, remember, the Z-score formula is Z equals the score minus the mean divided by the standard deviation. Right? And here we saw that, let's do Pam first. Pam scored an 1,800 on the SAT. That was a mean of 1,500 and a standard deviation of 300. So here we have for Pam 1,800 minus 1,500, right? 1,800 minus 1,500 divided by 300. And that gives us a Z-score of 1. And then for Jim scored 24. The mean for the ACT was 21. That's 24 minus 21. And then the standard deviation was 5. So Jim's Z-score was 0.6. So Pam's Z-score was 1. Jim's Z-score was 0.6. So who scored better, Pam or Jim? Pam did, right? Because she had the higher Z-score. And that's what we see. So if we were to make a normal distribution, right, with Z-scores, we would see Pam's Z-score is higher because it's further away from the center than Jim's is. Right? So we could do that. And that's actually what we call standardizing with Z-scores. So when we standardize, we take a normal distribution and we basically turn all of the values into Z-scores, right? We basically turn all of them in. Now, it might sound like a lot. I don't want to turn all the values into Z-scores. Well, that's fine, because all we have to do is we just have to find a couple of the values, like a couple of the key ones, not all of them, right? And in that example that we just did, those scores that we gave Pam and Jim, the 0.6 and the 1, those are like standardized scores because they're comparing them with other people, right? So this is just a refresher on z-scores. It's a refresher on it. We got the formula there. We got the formula there. We got a little definition of z-scores. So go back, look at it again, and kind of just get that refresher. You need to know z-scores to be able to move forward in this class. It's really, really important. And you also need to, get a refresher on percentiles, because when we look at percentiles are basically telling us what percentage of observations fall below a certain point. And if we were to map the percentiles onto one of these normal distributions, we would actually see something similar. Because let's say we wanted to say what's the percentile for Pam. She scored an 1800. Right? What was her percentile? Well, we could do that. We could find her percentile because, well, let me say it a little bit different. The way we would find her percentile would basically be to line everyone else who took the test up, see where she's standing, where Pam is standing, and then count how many people were less than Pam and divide that by how many people there were in total. But here, we don't know how many people there were in total. So basically, what we have to do is we just have to visually represent it. And when we visually represent it, this percent of people are less than Pam. Like, whatever percent that is, that's how many, whatever percent of the whole area, that's how many people are less than Pam. Whatever percent that is. And tying this back into what we did in the beginning, we said that the area is the probability, and we can see that the percentiles were kind of telling us the probabilities in a way. Right? That's what the percentiles were kind of telling us. They were kind of giving us probabilities. So whatever your percentile was, it was almost like a probability that you would land up in that section. Right? That's almost what your percentile is. It's like a probability. So here, Pam's percentile would be the probability, right, that we fit in this section, that we're somewhere in this section, because that is the percent of people, right? Or basically, Pam's percentile would be the probability that someone is less than Pam. Here's Pam. And Pam's percentile is the probability that someone is less than Pam, or that someone fits in that space over there. Right? So what we're going to do... Hold on. Sorry. I skipped a little too fast. We're going to look really quickly at that idea again of standardizing with z-scores. We're going to look at that one more time. Right? So let's say we had some situation. Whatever the situation is, let's go back to heights maybe. And when we do heights, we could draw a distribution. We know heights are normally distributed, so we're going to draw a distribution. And in the middle would be the mean. What's the mean height of, say, woman? Let's just do mean height of woman in America. What would you all say is the mean height? We've asked this question before. What would you all say is the mean height of woman in America?
5'7".
Like 5'7". Okay, we'll put 5'7". Well, let's go a little shorter. We'll go 5'5". Right, I think that's a little closer. Let's do it in inches. 5'5" is 65 inches. And previously, we had found that the standard deviation, I believe, was about 2 inches. So we would have 65 inches there, and then one standard deviation away would be 67 inches. 2 standard deviations away would be 69 inches, right? And 3 standard deviations away would be 71 inches. It's fine. Go in the other direction, 1 standard deviation away would be 63 inches. 2 away would be 61 inches. And 3 away would be 59 inches. With this value being in the middle. Now let's say we wanted to standardize this. Again, remember I said standardizing is changing all of the values from their numbers to their z-scores, or their standard scores. That's what standardizing is, changing all the numbers to their z-scores. Let's start with that Let's start with 67. Let's start here. What would 67's z-score be? What would the z-score be for 67? Well, z equals the value minus the mean divided by the standard deviation. For 67, that would be 67 minus 65 divided by 2, which equals what? 1. 67 minus 65 is 2, divided by 2 is 1. So 67 would have a z-score of 1. Can you all guess what 69's z-score would be? Anybody have a guess? Say it a little louder. Yep, it'd be 2. And what about 71?
3.
3. And what about 63?
-1.
-1. And 61?
-3.
Nope, not quite -3. We're not there yet.
-2.
2.
-2. And then 59?
-3.
-3. Right. So there goes our z-scores. And I mean, as you saw, like, we only got to do a couple of important ones. There's only one that's missing. What's the one that's missing? What would be the z-score of 65 inches? What's that z-score? Anybody?
0.
0, yeah. Right? We could put it in the equation if we wanted to. In the equation, we get 65 minus 65 divided by 2, which equals 0 over 2, which equals 0. But also, we could just think about what we're saying when we say, what's the z-score? When we say, what's the z-score, we're saying how many standard deviations are we away from the mean? So how far away from the mean is the mean? It's not. It is the mean. It's right there. The distance from the mean to the mean is 0, right? And you could see here why we would call something like this standardizing. Because now we have a situation where instead of 59, 61, 63, 65, 67, 69, and 71, we have a situation where we have 0 in the middle, and then 1, 2, 3 on one side, and -1, -2, -3 on the other side. When we standardize, right, when we standardize a distribution, a normal distribution, or any distribution for that matter, but we're talking about normal distributions, whenever we have a particular value that we care about, we also need to turn that value into a z-score as well. So let's say we were looking at this value right here. This is 68 inches. We need to turn it into a z-score. So we need to find the z-score for 68 inches. So what do? Z is going to equal 68 minus 65 divided by 2, which equals what? 3 over 2, which equals 1.5. So this z-score is 1.5. And then when we talk about that person who has a height of 68 inches, instead of using that person's height, we now use their z-score instead. Right? Their z-score becomes what we use instead of that person's height. So this, again, is that process of standardizing. What is this called? Anybody?
Standardizing with z-scores.
Standardizing with z-scores. We are standardizing our normal distribution. Right? That's what we're doing. We're standardizing it. Right? And the quick way that you could do it is, let's say we had this. There's a quick way you could do it. First, what does this mean? What I wrote here, what does that mean? We just talked about it like 10 minutes ago. This is a what? A normal
distribution.
It is a normal distribution with what?
The
With
mean
with the z-scores.
Somebody was about to say the mean of what?
32 and standard deviation of 7.5.
Yep. With mean 32 and standard deviation 7.5. That's what that is right there. Like, that's what that means when I wrote it. And how do we represent it graphically? Well, we draw a shape. There goes our normal distribution shape. And then what do we put in the middle? Well, that's going to be 32 because that's the mean. And when we standardize it, this just becomes 0. Done. We've standardized this. And now anything else we label with its z-score. So we could label one standard deviation above, right, and get what value we get for a z-score of 1 and what value we get for a z-score of -1, right? And we do 32 plus 7.5, which would be 39.5. And then we do 32 minus 7.5. So 32 minus 7 is what, 25? And then minus 0.5 is 24.5. So we get 24.5. Right? And now we've standardized it. It's standardized. It doesn't have to be a whole long thing. We don't have to write out every single one, unless you're explicitly asked to write out every single one. Right? But that's the process. That's the process of standardizing it. Right? And you need to know what it means when we get something like this. You need to know when you see that, what does that mean? And you need to know how to represent a normal distribution like that. Question: is this distribution standardized? Anybody? What does this mean? Look at this right up here. What did we say the other one meant?
Normal distribution of 0 with standard deviation of 1.
Almost, but you missed a word there. Normal distribution with what? A what of 0?
Mean.
The mean of with the mean.
Mean of 0 and a standard deviation of 1. So is this already standardized or not? Do we have to do anything extra to standardize this?
No.
No, we don't, because our requirement for it to be standardized, the only requirement is that our mean has to be 1. I'm sorry, scratch that. Our mean has to be 0, and our standard deviation has to be 1. That is the only requirement for it to be standardized. So once we have a normal distribution and we have a mean of 0, standard deviation of 1, it is now standardized. So now the question is, how do we use this? How do we use this? Well, to use this, we actually got to use this chart here. And there's a whole bigger chart, but I'm just showing a section of this chart. This section of this chart is basically what we call a z-score table. And the z-score table lets us calculate percentiles using this table once we know the z-score. So if we have a value and we find its z-score, we can then find the percentile based on that z-score using this z-score table. And I'll show you in a second how that works, but I just want to kind of explain what I mean here a little bit more. All right? So let's say we have a value, some value. We're measuring people's heights again. So our value is x equals 68 inches. That's our value. Step 2 is to turn our value into a what? Z-score. We want to standardize it. Turn it into a z-score. And what do we get? Well, let's go back up here. What do we get for our z-score? We're doing this first example with the heights. What do we get? We got 1.5 for our z-score. That's what we got. 1.5 for our z-score. All right. So we take our value, turn it into a z-score. So for this one, z equals 1.5. Right? We can sketch it. So let's sketch it. here in the middle, we had 65 inches. I'm using the first example. We were concerned about this value, 68 inches. This is 0. This is 1.5. Now it's standardized. And then the last step is to find the percentile for that value. So find the percentile. And again, the percentile is telling us what, right? What percent of everything is less than that. So this percentile would be telling us what percent of everyone else is shorter than that 68 inches. So let's show what we mean when we say find the percentile, just like we did with Pam, right? We're finding what percent fits in all of here. That's what we're finding. What percent of all of our values fit in there, in that section there? Right? That's what we're trying to find here. And how do we do that? We just use a table. You also have calculators that will tell you the percentile based on the z-score. You give it the z-score, and it'll tell you the percentile. But we want to use the table because I think using the table can help us a lot in understanding what it is that we're trying to do, right? That's what using the table can do. It can help us understand what it is we're trying to do. So we're going to use the table at first, at least. And then once we get an understanding of the table, then we can, go back and what's the name of it? So how does this table work? Let's go back here. How does this table work? First, let me show you like a big form of this table. Right, so let's do Z. I forget what website I've been using. It's like Z table or something like that. There we go. Z score table. Z-table.com. And they got these tables. Tables are big, awesome. There we go. So with our tables, we have two tables. We have a table that tells us values for when they are beneath the mean, right? Below, so like negative z-scores. That's this first table. And then we have another table for positive z-scores. But what you'll notice is that every single time, the table always tells us the percentile, right, of everything that's to the left of the value. Now, we know that's the definition of percentile, but again, these percentiles are all also probabilities. So each time, it's basically giving us the probability that we land in the area to the left of whatever value it is that we're looking at. And we have two tables for negative z-scores or for positive z-scores. So let's go back here. The z-score we were looking at was what? What's the z-score we're looking at here? We want to find the percentile of this one. Right, so it's P for this.
1.5.
1.5. So P for that section right there. What is the probability that we land in that section? Or what is the percentile for that 68 inches? So let's go back to our Z table. Now, would we be in the positive one or the negative one?
The negative.
Well, is our Z-score
Positive.
positive or negative? Our Z-score is positive, so we're in the positive one. So what we're going to do here, scroll down here, like I'm zooming in. Our Z-score table has two sections. It has this first section, and let me actually, what I'll do is this. I'm going to actually screenshot this so I can write on it. Uh-oh, it disappeared. Hold on. Let's try that one more time. Screenshot it. Plop that right there. There we go. So what we're going to do here, so I can write on this, there are two sections. There's this first row down here, and this first first column there, and this first row up at the top. These two sections are what let us find what particular z-score we're looking for. Now remember, when we did our z-scores, I actually did this one wrong. But if you remember when we did our z-scores, what was the round off rule for z-scores? We always needed to leave how many decimal places? We needed to leave
2.
2 every single time. This is why we needed to leave 2. Right? We need to leave 2 because this is how we use z-scores to find other values, to find the probabilities. So what this lets us do, with our two decimal places on this side, right? These are telling us the first two numbers, so like the whole number and then the first decimal place. And then on this side, it's giving us the last decimal place. So like on this table, let's say we want to find 1.12. So we want to find 1.12. What would we do? Go down here till we get to what? 1.1. Right? That's this part. 1.1. And then we need to go across here till we get to what?
12.
0.02.
0.02.
Because that's the 2. So it's like we're separating it. The first 2 digits come from here, and the last digit comes from here. So going across here, it actually just stays 0.0 something. It goes 0.01, 0.02, 0.03, all the way up to 0.09. It doesn't go past that. Right? So for 1.1, we go 1.1 and then over until we get to 0.02. So we're going down, 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 down. We end up here at 1.1. Then we go over, 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 and we end up right here. This is the value we're looking for. So we're basically looking for the intersection. So that's 0.02 going down, and this is 1.1 going across. So we're looking at the intersection of these two places. Right? That's what we're looking at, the intersection. And what is the intersection? Somebody read that number out to me.
0.8686.
0.8686. And that point right there, that value is the percentile, 0.8686. Or the probability that something is less than that 1.12 number. Right? So that was our example with the z-scores. So let's look back here. We were looking for what? What was the value we were looking for our height person? We were looking for
1.5.
1.50. Don't forget the 0.50. And 1 point, we need 2 decimal places. So what do we need to go down until? We need to go down until we hit
1.
Well, no, not 1.
1.5.
1.5, and then we're going to go over until we hit what? Well, it's the first one, 0.00.
0.
And so what value are you all seeing there for that intersection?
Can you say that again? We're going over to which one?
To 0.00, right there, 0.00. Because again, we're going 1.50. So 1.50 lets us go down and then over. That's what we're doing.
It's going to be 0.9332.
0.932332. Yes. And that value is our probability, right? Or our percentile. 0.9332. So y'all see it right there? That's the one that we found. And that becomes our percentile. So what's P? P is 0.9332. Right, that's what P is. 0.9332. So important note, one more time, just to make sure everybody knows and understands. Our z-scores, when we use that z-table, we are always, every single time, that table is telling us about this percentile, the percent, what does that value tell us? It tells us the percent of data here. Or another way of putting that is the percentile, this is x, percentile of value x. And another way of saying that is percent of data less than x. Right? And then the last way of saying that is the probability of being less than x. And that last one is kind of where we're going to, the direction we're going in. Right? That's the direction we're going in. Probability of being less than x is the direction we're going in. Right? What's the probability that when we throw a dart at this dartboard that is our normal distribution, that the value we hit is less than x? And when I say throw a dartboard at this random normal distribution, what I mean is like that question of there's a person walking in here, we want to know what's the probability that they are less than a certain height? What's the probability that they are taller than a certain height? What's the probability that they weigh a certain amount? Right? That's what we're trying to find. Now here's the question. This is always, the table is always telling us the probability that something is less than x, right? Less than our value x. How do you all think we would find this probability? Let's say we wanted to know. Let's say we were building a roller coaster, so to speak. Let's do roller coaster. Oh, that's ugly. Let's say we're building a roller coaster. And our roller coaster can only fit people who weigh less than, well, let's do more than. It can only fit people who weigh more than 95 pounds because, you know, people who weigh less than 95 pounds are too small for our roller coaster, right? So let's just come up with a mean weight. I think I'll just go with 175 or something like that, right? So 175 pounds, I'm just making it up. That's our mean weight. So we have in 175, comma, 20. Let's do a standard deviation of 20. Right? So that's our distribution. And we want our roller coaster to accommodate everyone who is bigger than 95 pounds. Right? That's what we're saying. Our roller coaster is only for people bigger than 95 pounds, which puts us at all of this section over here, because these are all the people who are bigger than 95 pounds, right? That's who these are. All the people bigger than 95 pounds. Now, we said using the table, it always tells us about the space where?
To the left of the mean.
Exactly. To the left, well, not of the mean, to the left of the value we're concerned with.
Value.
Right, but in this case, we don't want to know about that space over there. What space do we want to know about? We want to know about this. That's what we want to know about, the space over there. Anybody have an idea of how we could find that? Anybody have an idea? How could we find the space on the other side? The table tells us the space to the left. We want to know about the space to the right. Any ideas? Okay, let's think about this like a cookie. If you have a cookie and you got to share this cookie with your sibling, right? If your sibling gives you this much of the cookie, how much of the cookie did you get? which portion of the cookie did you get?
A larger portion.
No. I'm sorry, which portion did they get? Not did you get. Which portion did they get? You got that
Subtract.
little orange portion. Which portion did you get?
The smaller portion.
The smaller one, and they got the yellow portion, right? So, with that, how could we find out? Let's say the whole cookie, right? Let's say the whole cookie was one whole cookie. Right? The whole cookie is one. They gave you a quarter of the cookie, 0.25 cookies, right? How much is left over for them? How much did they take for themselves?
0.75.
0.75. And how did y'all do that?
Math.
Oh, man.
Subtract. My bad. I'm sorry.
Subtract. The whole thing is 1. You take away 0.25. What are you left with? 0.75. So it's almost like this little section was 0.25. This big section was 0.75. And the whole thing was 1. And with probability, what did we say the probability of the whole sample space was? The probability of the whole thing. What's the probability of the whole thing? Of everything? Anybody remember? What was the probability of everything? Well, think about it this way. Here we're doing weights. Whatever you weigh, you got to be somewhere on here, right? You got to be somewhere. Either you're all the way over here or somewhere, right? You could be here, 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 anywhere on there. But this thing accounts for every single, our distribution accounts for every possible weight, doesn't it? So what's the probability that someone weighs a possible weight? Well, they have to weigh a possible weight, don't they? So what's the probability that they weigh something that's possible? Probability that someone weighs a number that's here. What's that probability? That's something that's always going to happen.
100?
100%.
Well-
Or another way of saying 100%.
1.0.
Yeah, 1. So the whole thing, all of this is 1. That whole thing is 1. And if we know what this is, we can subtract that from 1 like you all did with the cookie. And that will leave us with this section over here. Right? So how do we do this? Well, we go through the process just like we did. When we go through the process, right? When we go through the process, it's going to give us this little section here. That's the section that the process, the P that we get from the table will give us that little section. But what we want is, we want this big section. This is what we want. Right? So P from the thing is going to give us a little section. We want the big section. So when we do it, we're going to get P. That'll be P. And what do we need to do to find this? This is going to be 1 minus P. Okay. So whenever we want to find the value to the right of the line, we just do 1 minus the probability. Right? That's all we do. 1 minus the probability. Let's do another scenario. Let's say, instead of just saying we want the value to the right or to the left, let's say we were concerned instead, let me move this down a little bit so we don't get confused. Instead of saying we want the value to the right or to the left, let's say we were like, we want to know what percent is in the middle. Right? Remember, we said the whole thing is 1, and the table is telling us, right, is telling us about the space to the right. Every time we use a table, it's going to tell us about the space to the right. So we want to know what's the probability that we land in between two values, x1 and x2.
I thought the table told us everything to the
I'm
left.
sorry. Did I say to the right?
Yeah.
I'm sorry. Thank you very much. That's just my sleepy brain. The table tells us everything to the left. Thank you very much, Danita. Yes, the table tells us everything to the left. Um, so here, how could we figure out what was in the middle? Well, I mean, we could just start going through the process. We could take x1 to find z1, and then use that first z-score to find probability p1. Where would that probability p1 be sitting? That would be this over here, right? This would be p1. Okay, we could do that. And then what about this right here? For everything over here. P1 is everything here. Well, we could do the same thing. X2. Turn that into Z2. Turn that into P2. And that would be everything over here. That's P2. Everything from the line all the way over. And what could we do? What could we do to find that yellow section? We know from x2 all the way over to the left, and we know from x1 all the way over to the left. So what could we do? This space in the middle, which is the p that we're looking for, what could we do there to find that value? Any ideas? Any way we could use math, in the words of Danita? Any ways we could use math to find it? Come on, somebody think of something. Brainstorm out loud if you got to brainstorm out loud. Brainstorm out loud.
Subtract something.
Say that one more time.
Subtract something from something.
I would say X1 from X2.
Exactly. Like, think about it, right? X2 is this whole space. What do we need to take away to get the piece in the middle? If we draw a line here,
X1.
we need to take away this space. So what we need to do is we need to do x2, what we get from x2, and take away what we get from x1, right? So to find that space in the middle, we do P, the probability is going to equal P2 minus P1. The probability we get from x2 minus the probability we get from x1. Right? So yeah, exactly. Do some subtraction. That's the subtraction we need to do. We have one more kind of scenario that we might run into. And this last scenario that we might run into is a scenario like this, where we have our normal distribution. And this time, we're trying to find that, and not what's in the middle. What could we do here? Let's see how sharp you are getting. And this is x1, this is x2. This is going to give us some kind of P1, while this one is going to give us some kind of P2. So what can we do to find how much is on the outside? Come on, brainstorm out loud. Out loud means not on mute.
We're looking for the outside, like the yellow.
The yellow. We want to find the yellow.
Would you divide?
Nope, no need to divide. This is all just adding and subtracting.
So to find everything for the X1 to the left, if we're subtracting.
Okay,
we
so
can use the.
You add one in X1 and X2.
Almost. It's almost like
multiply.
adding. Nope,
multiply
nope, no,
X1
no,
and
no.
X2.
We're not multiplying anything. We need to add, do some
Uh-uh.
addition and some subtraction. So we need this section. That's a section that we want. That's easy. So that's going to be P1. Okay, we got that. That part's easy. Now, what are we going to add to it? How do we find this section over here? Can we look back at one of our
We
rules?
add them both and then subtract one, or what?
We're adding X2
How do we
to
find
X1.
the space to the right of a line? What do we say we need to do to find the space to the right of a line?
We gotta add
We
both.
subtract one from,
One minus those.
One
yeah, one
minus it,
minus.
exactly. So we do P1 plus 1 minus P2. P1 is this over here. 1 minus P2 is that section right there. Right? Because this whole thing was P2. All the way to the left, right? All the way over here. That's all P2. All of this is P2. And this whole thing is 1. So this section here is 1 minus P2. That's what this section is. This section is 1 minus P2. And again, P2 is the value that you get when you use the table and you put an X1. Right? That's the value that you get. And again, whenever we use the table, we're starting off with an X value. We standardize it into a Z-score. And then we turn that into a probability. We could also go the opposite direction, which we'll talk about, but the opposite direction would be starting with some probability or percentile, turn that into a Z-score, and then turn that, I should have actually done it backwards. Let's do it the other way. We start off with a probability, turn that into a Z-score, and then turn that into an X value. So we could do it both directions. But this is getting us the relationship between the value that we have and probabilities, right? We're getting literal relationships between values and probabilities. And this will empower us to find almost any kind of probability that we may want to find, right? That's what this is going to empower us to do. So let's go back here. Let's do a couple of examples, and then we'll be done. So we're going to go over here. And we're going to kind of walk through the examples. I think they have, I'm going to send you all another video that has some more examples in it. But we're going to kind of walk through it a little expeditiously. So here, this is a quality control example. So it says, at Heinz Ketchup Factory, right, the amounts which go into bottles of ketchup are supposed to be normally distributed with a mean of 36 ounces and a standard deviation of 11 ounces. Right, so already from there we can write this. In 36, 11. I'm sorry, not 11.11, right? Because that's our normal distribution. Once every 30 minutes, a bottle is selected from the production line. Its contents are noted precisely. If the amount of ketchup in the bottle is below 35.8 ounces or above 36.2 ounces, then the bottle fails the quality control inspection. What percent of the bottles have less than 35.8 ounces of ketchup? That's the question. What percent of the bottles have less than 35.8 ounces of ketchup? Well, what's the first thing we should do? An idea of the first thing we should do that'll help us? Draw a picture. We should draw a picture. It's the first thing we should do. Let's draw a picture. Right, so we're going to actually do it over here. So for our picture, we're just going to draw our normal distribution. Get used to drawing these. You're going to draw a lot of these. So here's our normal distribution. We said in 36, 0.11. What goes in the middle?
36.
36 goes in the middle, right? And when we standardize it, that 36 is going to become
0.
0. 36 is going to become 0. Now, what else do we need to draw? We need to draw the places that we care about. What's the value that we're trying to find? We want to know what? What percent of the bottles have less than 35.8 ounces of ketchup? So when we draw it, what marker should we make on this picture here? What marker should we make? We want to know what percent is less than 35.8. So we should mark what on our graph, on our image?
35.8.
35.8. So let's mark 35.8. So there goes 35.8. Now we need to continue standardizing it. When we standardize it, what do we get for 35.8? Well, z equals x minus the mean divided by the standard deviation, which is going to equal 35.8 minus 36 divided by 0.11. And what do we end up with? 0.2 divided by 0.11, which equals, calculator, 0.2. Well, let's just put the whole thing so y'all can see it. 35.8 minus 36. Divided by 0.11. And what do we end up with? Negative 1.818. And it continues. So when we round this, we get negative 1.82. So we got negative 1.82 as our z-score. Negative 1.82. So this is the z-score we are concerned with. Now what do we do with our z-score? Let's go back up here. Let's go back up. What do we do with our z-score? Let's go down a little bit. I went too far up. Right. We start with, I just had to go up a little tiny bit. We started with x. We turn that into z. And then we need next find p. But before we do that, let's label off the section that we care about. The question said, what? Which section should we mark off? This is 35.8. Which section should we mark off?
35.8.
We marked 35.8, but remember we need to do a percentage. We need to do a section. So what's the question asking us? What percent of bottles have less than 35.8 ounces of ketchup? So which section are we going to mark off? Which section should I highlight here as the section that we care about?
Everything to the left of the 35.8.
Exactly, because all of this stuff over here, this is what's going to be less than, right? That's what it is over here. That's less than 35.8. And so now we need to go into the table, right, and find the percentile, the p-value for that negative 1.82. So I want everybody to go on to ztable.com, z-table.com. Go to z-table.com. And for this, should we be in the negative tables or the positive tables? What's our z-score again? Negative 1.82. So should we be on the negative tables or the positive tables? Anybody? Negative tables or positive tables? We're concerned with negative 1.82. So should we be on the negative tables or the positive tables?
Negative.
Negative table.
The negative tables. And when we look on the negative tables, on the left column, we're going down until we get to what?
1.82.
No, 1.8.
Down to 1.8, exactly. And then we're going across until we get to
Two.
0.2.
0.02. And what is the value that we get?
0.0344.
0.0344. So for this, P equals 0.0344. So for over here, we got 0.0344. And another way of putting that is 3.44%. So the question is, what percent? That was our question. What percent of bottles have less than 35.8 ounces of ketchup? So what percent have less than that? 3.44% have less than 35.8 bottles of ketchup. Right? So remember, we said everything outside of that range is going to fail. If it has less than 35.8 ounces of ketchup, it's going to fail our inspection. Right? So is that the question we would have to ask ourselves now? Right? Is that 3.44% of loss? Is that worth it or not worth it? Right? That's the question we'd have to ask ourselves. Is that 3.44% of loss worth it or not worth it? Right? Because they said the bottle fails the quality control. Right? So I'm guessing if you have too many of it, then you're like, oh, wait, that's not enough. But I mean, I think 3.44% of failure, that is a pretty low failure rate. Right? That's a pretty low failure rate. But this is like a real life-ish example of how we would use this. Right? That's what that is. And swipe through it, blah, blah, blah. You can see they did the exact same thing. Right? And then the next question, was what percent of the bottles passed the quality control inspection? Right? So for this question, this is actually one that I would like you all to try to do, because the ones that pass the quality control inspection are going to be the ones that are between what two numbers? They're going to be the ones that are between 35.8 and 36.2. Right? That's what it's going to be in between, 35.8 and 36.2. Now you'll find something is a little interesting when you actually do it. You'll find that there is quite a bit of symmetry. So whenever you find symmetry with these normal distributions, because they are symmetrical, that symmetry does definitely come into play. Right? So here is almost like the opposite, and it's really similar. I'm going to kind of walk through it, and then that'll be all we do for today. But it's kind of like doing the opposite, where we get a percentage and we want to find the z-score and thus the value. So here it says body temperatures of healthy humans are distributed nearly normally with a mean of 98.2 degrees Fahrenheit and a standard deviation of 0.73 degrees Fahrenheit. Right? So our normal distribution looks like what? In 98.2, comma, and 0.73. So that's our normal distribution. What is the cutoff for the lowest 3% of body temperatures? Right? That's what we're asking. What is the cutoff for the lowest 3%? So if we go down here, let's say we're trying to do our body, let's draw our normal distribution. We always start there. Always start with drawing a normal distribution. So now we have one drawn. And we want to know what the cutoff is for the lowest, lowest 3% of body temperatures. So we want to find what X value gives us, what X value works such that P equals 3%. Right? What X value works and gives us a P of 3% or 0.03. That's what we want to find. What X value gives us a P of 0.03. So we do the same exact thing that we did before. Let's write our normal distribution. We said 98.2, comma, 0.73 for our two things. In the middle, we're going to have our 98.2, right? We don't know, we can't do a standardization because we don't know We don't know what this x value is. That's what we're trying to find. We don't know what that is. So what do we have to do? In this case, we have to start with our percentage, change our percentage into a z-score using the table, which I'm going to show you how to do in a second, and then change our z-score that we find into an x value using the same formula we use for z-score, just in reverse. So how are we going to do that? Well, let's go into the table. We want to find the z-score that's associated with 0.03. So we're going to go in the table. We're going to use the table in a little bit of an unintuitive way. So first things first, right, we need to ask ourselves, are we in the negative side or the positive side? Here's a hint. If our percentage is less than 50%, we're on the negative side. And if it's greater than 50%, we're on the positive side. 50% is that middle point, right? So less than 50%, negative side, greater than 50%, positive side. So what we're going to do here is a little unorthodox, but we're going to kind of dig in the middle. We're going to look through the middle massive numbers, and we're going to look for the closest number we can find to 0.03. Right? So what's the closest number we can find to 0.03? And as we start going through it, right, we can see we're at 0.139. No, we got 0.288, 0.222. We're kind of going up here. We got 0.0359. That's kind of close. 0.0344. No, we can even get smaller. 0.0329, 0.0322, 0.0314, and we have 0.0307, 0.0301. That's like almost exactly 0.03, isn't it? Like that's really, really, really close. So that's the one that we're going to go with. 0.0301 is the one that we'll go with. And we are at 0.0301, right? Now we basically make a note of where it is, and we see what row is it in, right? And how far up is it? What row and what column is it in? So we can see that 0.0301 is in the minus 1.8 row, and it's in the 0.08 column. Y'all see that? Y'all see that?
Yes.
Okay. So
Yes.
we were in the minus 1.8 row, right? And we were in the 0.02. Was it 0.02 or 0.08?
0.08.
0.08.
We were in the 0.08 column. And I mean, if you have been kind of watching and you have that intuitive sense, you can see clearly where this is going. It's going to be negative 1.88. But if you don't and you need me to like lay out a step, you can just add these two numbers together and you get 1.88. Or take this number and add it to the end of this number. Like, there's no difference. Right? We just add an additional number there. So we get 1.88. I'm sorry, negative 1.88. Right? And that is our z-score. That's the z-score that corresponds. So we started off with 0.03. Turn that into negative 1.88. Now we need to figure out an x value. How do we figure out an x value? Well, we started off with this z-score formula. Z equals x minus mu divided by sigma. Well, now we just need to mix it all up and flip it all around. And what we end up with is x equals z times sigma, right, plus just the mean. Z times sigma plus the mean. So that's what we end up with. And that gives us the x value. So for here, z is negative 1.88, right, times sigma, so negative 1.88 times sigma, which was 0.73, right, plus the mean. The mean is, let's go up a little bit, 98.2. And what do we end up with? Do I even remember what we had? We had negative 1.88 times 0.73 plus 98.2. And we get 96.827 or 96.83. Sorry, 96.83. And that's the cutoff point for the bottom 3%. That's the cutoff point, right? So the value, the x value here, is 96.83. Right, so that's going in the opposite direction. And all the other stuff is involved as well. You see, we got it there, 96.8. And the rest of this is just like some practice examples. When we have normal distributions, this is just a recap of that 68, 95, 99.7 rule that we had done before. This can be very helpful because you might find that something falls exactly one standard deviation away from the mean. And if it does, then that makes all your calculations a little bit simpler because you don't have to do the same calculations for percentages. You don't have to do the same calculations for z-scores and whatnot because they're all just nice, simple numbers. When we use our table, if we have something that's not on the table, right, just put the highest number that you see on the table. So like, I think that table goes up to a z-score of like 3.99. So if you have something that has a z-score of 3.99 or 4.35 or something, just put the percentage that you saw for 3.99. I think that percentage is like 0.99999, and then on the other side is like 0.00001. Moving on, we're gonna stop there. That's where we're gonna stop. You can look through the rest of this. I think it kind of just, it's pretty straightforward stuff. So you can look through the rest of this, but we will stop there. Right, and we did the cutoff points example already. And again, I'll send a video that goes through some examples, and we'll also do some examples in class next week.